So coming back to the population, for I find out who the neighbors are, and let's say the neighbors of I were W3 and W5. So, and something else. So let's just tick which were probably the neighbors. It was 3, it was 6, and let's say these were also the neighbors. So out of these neighbors, I select two random parents. So the red ticks are the ones which are from a pre-computation known as the neighbors. The neighbors are actually in the weight space, not in the population space over here. But then I told you why taking the individuals which are close in the weight space is also okay. So the red ones are the neighbors in the weight space. So for WI, these were the three neighbors, and I just select them up, and I select any two as the parents. So let it be this one, and let it be this one. Of course, I do a crossover and mutation. So let me write down the conventions here. These are neighbors in weight space, and these are selected parents from neighbors. So I've got the same parent. I'll do a crossover. I'll produce the children. These are the same parents over here, just to clarify. So this is taken from here and this is taken from here, and this one is of course a crossover. I do a mutation. And let's just concentrate on one individual over here as the child. Okay, now for ith parent, I've got a child. So first of all, a parent will fight with child. That's what we've seen always. The parent fights with child. So I say child C replaces parent I if better. And the term better means that ith child, which function is it solving? It's solving GWIX. That's a function it's solving. So C needs to be with a better value as compared to the original parent, which is xi. So if, then you say xi is equal to C. And of course, what is GWI? It can be rewritten as if WI, which is the ith weight, dot f of C minus utopian point is less than, what's the G function? WI f of xi minus utopian point, then you say xi is C. So it replaces better. However, the child C may be better for any individual. The child C may be better for any individual. So I should actually go and check if child C can also replace this individual, this individual, this individual. Every individual has a separate and different objective measure, and therefore the child C can replace all the individuals possible. Now, if you do this, your complexity will of course become extremely large. So I say that first let's filter out all the individuals. Which individuals are likely to be affected by the child C? Only the neighbors, only these red colored neighbors. Because for all the child C is close to the parent in the weight space. and these red ones are close to the parent, so the red ones I and C are close to each other, so it's possibility that accidentally you may have found a better solution. However, for something like this and this are two very different weights. That means a minor mutation of this is unlikely to produce a better solution for this, because these two in weight space are very far away from each other. And therefore, I will compare C if it can replace this one, C cannot replace this one, C cannot replace this one, C cannot replace this one. I'll check that if C can replace any of these individuals, then I will go upon replacing the same up, and that is the entire fundamental of the multi-objective evolutionary algorithm by decomposition as an algorithm. Now, there are two things to be added. The first thing is utopian point is not known. The solution is, instead of finding it out, you optimize utopian point as you go. So with this, I will try to create in an algorithm that we'll call as the multi-objective evolutionary algorithm by decomposition. So let's start off with the obvious thing. So the first thing that we of course did was generate n random weight vectors. No change in the algorithm, and those will be Wi, of course, the set of all random weight vectors. And of course, it's not only random, it's also some heuristic that makes it diverse. Now, in the algorithm, we were relying on neighborhoods like this. So we were relying on neighborhoods like this. So, and I said that neighborhood calculation can be hard. So instead of doing it in any kind of loop, I say calculate the neighborhood of all weights. Calculate neighborhoods of all weights. So that's a simple rank formula. So you calculate the distance of Wi with all the individuals, and then calculate the nearest k. You know, it's a proximity query, so there's a KD tree data structure that can make it more efficient, but we calculate the weight, the neighborhood function, and this is something that will be used many times. So because I'll be using it many times, I write it down once over here, and then I need to create a population pool. So I say my population pool is X, which is random Xi for all I. So random individuals, that's exactly what you do in the genetic algorithm as well. So initially, yes, I have already divided it into n single objective optimization problem, but to start off with, all of them will have a random solution. So this is the one that optimizes W1. It'll have a random solution, W1 times Fx minus U1. It'll have a random solution. The second one will have a random solution. The third one will have a random solution. The fourth one will have a random solution, and so on. So initially, all of them have a random solution. I will optimize that along with time. Now the thing is that I invoke this assumption, utopian point is not known, so I have to optimize utopian point as you go. What better way than do it right now? So I say the utopian point is equal to the minimum value over the jth dimension for all dimensions j. So the jth dimension, that means the jth objective function, the lowest value of the jth objective function. So the lowest objective value of the jth objective function Okay, there I need to do it. Okay, let me write it down in a simpler term. So the utopian point is nothing but u1, u2, u3, all the way up to um n dimensions, where uj is given by the minimum value of the jth objective function. So the minimum value and the jth objective function for all individuals I. So I minimize over all individual. I look at all the individuals in the random population pool, whichever individual has the lowest value for the jth objective function, I take that one as a utopian point. So that's just guessing the utopian point from all the individuals which are around over here. Now is where my main loop starts. So I say while stopping criterion, I'll write down the code for one individual and I will repeat it for n times. So to population size. So population size is n. So here what do is I'll write down the code to generate a better child for the ith individual, which can also update the other parents as well, by the way. And I'll repeat I from 1 to n, so it'll do it for all of them. Now here is where my main function and my main logic starts. So here is where the critical things start. The first thing is I need two parents, parent 1 and parent 2. Normally I would have there's no objective function over here, so normally I would have taken random parent. So let's take a parent 1 and a parent 2. Normally I would have said is that parent 1 is randomly taken from a uniform distribution for between 0 to the population size, and similarly parent 2. But then this will be extremely bad because I know that neighbors of I, which I've already calculated around over here, I know neighbors of I are much better candidates to give me a better solution for the ith individual. So parent 1 is taken from a uniform distribution of the neighborhood of weight I, and similarly parent 2 is taken from the neighborhood of weight j. So that means two weights which are close to each other are two weights which are close to the weight I will give the two parents. Then of course I do a crossover and a mutation. So let's say parent 1, parent 2. So I do a crossover of parent 1 and parent 2. It gives me two individuals. I take one of them and I mutate it up, and that gives me my child C. Okay, now there are too many things to be done. So should the child replace the parent? And second is that the utopian point needs to be learned. So let's do something which I have done already, which is here. So let me replicate this line. So do I have a better utopian point? So I'll just write down this line again. Utopian point is easy. So I say I'll have to do it for all j, like here it was done for all j. So for j is equal to 1 to number of dimensions, which is m. So the utopian point j takes in a minimum of the old value and the new value, which is f of j, the jth objective function, and the new child which is generated. The jth function and the new child which is generated. So that's the utopian point. Learning absolutely very simple. It's just a replication of the previous lines if I get a better utopian point. But the harder thing is now I'll have to check whether child replaces individual 1, whether child replaces individual 2, whether child C replaces individual 3, whether child C replaces individual 4. So normally I would have gone for j is equal to 1 to all the individuals which child C can replace the entire population size, but that will be too computationally expensive. So let me say I only restrict to neighbors. I only restrict to neighbors of weight of I. The others I'll not check. The chances of it happening are small. Then I check if child C is better, so G function, the objective function parameterized by weight J of C. I'm using C and F of C interchangeably. You use one consistently. Either define the function G on the individual or on the objective function value. So if C is better than the old individual, which is X of J, so if it's better than the old individual which was generated here, which is X of J, then I need to just update it up. So X of J will become the new one, which is C. And similarly, I'll do it for all over them. And this is my entire code. So let's look at the entire code once more. So here what did I do was, the algorithm is still very simple. All that I did was, line number one, the most important, I break down a multi-objective optimization problem into n single objective optimization problem over here by generating n diverse weight vectors. Then I calculate the neighborhood, that will come later. Then I generate a random population, of course, and I try to learn the utopian point. Now, let me just remove the lines of the utopian point because it is too obvious that the utopian point will continue to learn itself. So this is from the current population, whatever utopian point that I got. So the jth coordinate of the utopian point is the minimum value of the jth objective function, or fj, for all the individuals that I've seen. So currently I've seen n individuals. So for all n individual, I find out which one has the lowest value of the jth objective function, and that will be the jth coordinate of the utopian point. And similarly, when I see a new objective function, when I see a new individual, I check, have I seen a better value of the jth objective function? If yes, then I replace it up. So that's a unfortunate learning of the utopian point because there was no other way to get that. The main logic is x1 will be the objective problem with weight 1, x2 will be the objective problem for weight 2, x3 will be the objective problem for weight 3, and so on and so forth. So all that I do is that in order to solve the problem, I solve it for one xi and I repeat it for all i's till the stopping criterion. I carefully select the parents from only the neighborhood because I know close parents make close children. And then I produce the child from the parents. So this is normal GA. And this is normal utopian point learning. So that's normal utopian point learning. And this is normal GA. So if you really look at it, the algorithm is only over here. So you say that a child is generated because for the first time, every individual has a different objective function. For the first time, every individual has a different objective function because it has a different weight. So the child C checks for all the individuals if for that individual, that objective function, it is better. For the first objective function, is it better? For the second objective function, if it's better. If it's better, then it replaces the parent. It can replace any number of parent. And there is a neighborhood restriction because otherwise the complexity will turn out to be too large. That's the entire algorithm, the multi-objective evolutionary algorithm by decomposition. So all it does is that it keeps on generating individuals and then it keeps on seeing whether that individual is better for any of the n objective functions. If yes, then it accepts it for the parent, otherwise no. And the algorithm runs in that manner. And this line again is fancy to write down, but it's nothing but wi times f of c minus utopian point u is less than wi times, in fact it's j times f of x of j minus the utopian point u. So this is that condition. And that's why you see that this utopian point was being learned. If it's better, it replaces. Now, of course, later on I'll also have to find out. So let's say this gives me So let's say that I run this algorithm, and so there are weight vectors like this, and I get this as the optimal solutions of the n objective functions. So representing that in a space without in the objective space without drawing the lines, it turns out to be like this. Now, of course, I need to use inverted generational distance, for which I need this, which is the true Pareto front. And how do I generate that? Luckily, for most problem, it will be given if it's already a standard problem. But then if you want to generate it up, so let's say E is the external population, which is the... So let's say I have E, which is the external population, and the external population is the one which is my ideal Pareto front, dense Pareto front over here. So initially it is nil. Initially I don't have any individual around in my external population. Now what I do is, whatever individuals come around over here, whatever new individual C comes around over here, I check if it is worthy of putting in my external population pool. So if C is not dominated by any individual, so if C is not dominated by any individual, in E, then it's good enough to add. Here I don't have a size restriction, I need it extremely dense. Then add C to E. Now sometimes an individual that's already in the Pareto front may be bad, so I need to delete it up. So I add that line as well. If any individual E in E is dominated by C, then delete E from E. So this is maintaining external population on my true dense Pareto front. Let's look at it maybe directly as maybe an example. So let's draw an external population pool around over here. So initially it's empty, I generate some C and I keep on adding that up around over here. Now suddenly a C, this is found. So suddenly I get a C which is around over here. So that's my C. Now if you look closely, this C dominates these two individuals, so they need to be deleted. They are no longer non-dominated. So that's what I see, that I say that these two are deleted. On the other hand, what happens is, in a different case, I have now this individual and a C comes which is around over here. Now C is dominated by these two individuals, so it will not get added in the Pareto front. It is not non-dominated. On the other hand, a C gets around over here. Now C is not dominated by this, C is not dominated by this, C is not dominated by this, C is not dominated by anyone, so it will be a valid member of the external population, and you keep on doing it up, that's when a lot of individuals will actually get added, and you'll get a dense Pareto front as the evolution goes along. So you'll get the solution by the MOEA D, you'll also get the dense Pareto front or the external population. So nothing added in the code, you start off with an empty external population, and you keep on adding it if it's non-dominated, the child, and you keep on deleting it if the child dominates anything in the Pareto front. And with a mixture of all this, the multi-objective evolutionary algorithm by decomposition works. Here it's more interesting to see how the algorithm will act with time. So all that will happen is initially the individuals will be up at random, and slowly they'll start coming into their respective fitness function value. So one individual which is x1 will start coming around over here, one individual which is x2 will start coming around at this line depending upon the weight. So they still show a nice transition to a Pareto front, and the diversity is always maintained because the weights are what are diverse in nature. The basic fundamental only that multi-objective optimization problem can be broken into n single objective optimization problem that are solved independently. They differ by the weighted function addition of the single objective optimization problem. They have different weighted addition, different weights for the weighted addition of objectives. And thereafter we said some sharing of information should be possible. So if solving the ith objective function, I generate accidentally a better solution for the jth objective function where j is a neighbor of I in the weight space, then I say, okay, you take the better one. Not only I maintain myself, you also maintain yourself. An individual is better for you as well. There's a better individual for your objective function as well. So this kind of sharing made it possible that a child generated randomly not only replaced or tried to replace its own parent, it also tried to replace or optimize or benefit the neighboring parents. And that's how I got in a diverse set of individuals on my Pareto front. And thereafter, of course, there'll be a knee analysis, there'll be a multi-criterion decision making, learning the user preference, and all those things that will say out of these n individual, which one individual the machine or the user selects, which will be finally implemented as the phenotype, as a solution to whatever the optimization problem was being solved by this algorithm.